Hey guys, this is Alan here to do some more FE review on linear systems, and specifically this video will cover the topic of Laplace transforms. Alright, first let's talk about why we need the Laplace transform. What's its purpose? When performing DC circuit analysis, we didn't need the Laplace transform because we could easily handle expressions like for the current through a capacitor, because the current through a capacitor is represented by the capacitance multiplied by the change in the voltage over time, but there is no change in the voltage in a DC circuit. So your C times dV dt was always 0. And so we could just model that as an open circuit wherever we had the capacitor, and then we could easily handle the voltage across an inductor, because the voltage across an inductor is calculated with the inductance multiplied by the rate of change of the current with respect to time. But in a DC circuit, there is no change in the current with respect to time, so this expression was always 0, and we could model the inductor in this circuit at steady state. Well, I say steady state is DC, so it's always in steady state, but we could model it as a short circuit. In AC circuit analysis, the presence of a time-varying voltage and current leads to the use of non-homogeneous differential equations, and nobody wants to solve those. I know that those are going to be on the FE, and that's a specific area of weakness for me, and I'll have to get on those pretty good before I take it. But the Laplace transform is awesome because it eliminates the need to solve these differential equations. And when you transform each expression in your, say you've got you're using KCL or KVL, and you're doing nodal analysis or mesh analysis, you can represent each one of the components in the circuit in the S domain, and you can just use algebra, and it's much better than having to deal with the differential equations. Alright, so let's look now at the next slide. Let's look at the mathematical equation for the Laplace transform. It's possible to calculate the Laplace transform of any function, and we'll use f of t representing the function, using the equation f of s, which is your Laplace transform, equals the integral from time equals 0 to infinity of f of t, which is the function you're trying to transform, multiplied by e to the negative st, and then dt. Now, why e to the negative st? To be perfectly honest with you, I don't know. And it's not important for you to know either. Leave that for the math majors. Just know that when you do this, when you perform the Laplace transform, and then you perform your nodal analysis or your mesh analysis, and then you get at the end of the problem, and you undo your Laplace transform, which we'll talk about in just a minute. It works. Some geniuses came up with this. So for some simple functions, if you wanted to calculate the Laplace in this way, it's relatively easy to do. But in most applications, the extra time and the added potential for you making a mistake is unnecessary and even unwise. Therefore, we'll usually rely on tables of transform pairs instead of calculating the Laplace transform for ourselves. Alright, moving forward, let's look at some common Laplace transform pairs. And you can see that we've got a table shown here to the right of those pairs. And for some of you, even looking at the f of t, like the functions that we're trying to transform, you look at those and you think, God, those are ugly functions, or they're uncommon functions. But that's not true. Those are actually very common input signals for circuits. And you can see down there where you've got the sine omega t and the cosine omega t, and so you've obviously seen those used as inputs a lot. But then you've also got your step function signal, and you've got your ramp, and you've got your unit impulse, and all these things you're going to see them, and you can see the Laplace transform for each over to the right. All right, let's keep on rolling. And talk now about the inverse Laplace transform. All right. Use of the Laplace transform for AC circuit analysis goes kind of like this. Now, the first thing you would do is you'd convert all the time domain expressions to the S domain using your Laplace transform. You'd perform necessary algebra to get the desired value into a relatively simple S domain expression. When I say the desired value, it could be anything. Like, let's say the question is asking you for the current through, a particular resistor, or the voltage, between two particular points. Right? That could be what you're looking for, and that can be expressed in the S domain. And so that's what you're trying to do. And then once you get that, whatever it is you're looking for, in the S domain, you're going to use the inverse Laplace transform of that expression to get it back into the time domain. You can't just leave it in its Laplace transform, because that doesn't mean anything to anybody. You got to get it back to the time domain so that it makes sense. Then it'll be a usable expression that allows us to calculate values of current or voltage, or whatever we're looking for with respect to time. And I made that sound pretty easy right there. You just perform the inverse Laplace transform, right? Piece of cake. Not always. The inverse Laplace transform can be tricky, because oftentimes you'll have an expression that is true. It's an S domain expression for a particular voltage. Let's say voltage, and it's true, it's right, but it's not simplified in a particular way that allows you to figure out how to perform the inverse Laplace transform. So you'd be going, let's go back to our previous slide real quick. Let's look at that. All right, so you'd be on the right side of this table, and you're looking at these functions over here in the S domain, and you're looking at the one that's on your paper, and you're thinking, golly, mine doesn't look anything like that. And the problem is trying to simplify what you have in such a way, and I say simplify, but I mean, it's not going to look much more simple. But you've got to get it into such a form that mirrors one of these, so that you can recognize which one of them you're going to use to get it back to the time domain. And that can be tricky sometimes. So that's something that you'll need to practice to make sure you're familiar with how to do that on the FE. But that's the basic idea of what's going on. Let's look now at two theorems that are potentially useful to you: the initial value theorem and the final value theorem. And these describe relationships between the time domain and the frequency domain, or I say the S domain. And the initial value theorem states that the initial value, and that's time equals 0, initial of a time domain function is equal to the limit as s approaches infinity of f of s. All right, what does that mean? It means f of s is your Laplace transform. All right, so whatever your expression for your Laplace transform is, throw an s in front of that, a factor of s, all right, in front of that, and then calculate the limit of that as s approaches infinity, and then that'll give you the initial value of the time domain function. The final value theorem, which is important for steady state analysis, states that the final value of a time domain function is equal to the limit as s approaches 0 at s multiplied by f of s. And I want to point something out here that helps me remember these, is that it's when you're looking for the initial value, you actually solve for the limit as s approaches infinity, which seems a little counterintuitive. And then when you're looking for the final value, you're using the limit as s approaches 0. So that's not a typo, guys. We didn't get that mixed up there. That it actually is the opposite than what you might think, but it works. So there's a lot more that goes into this also, guys. Primarily practicing using the Laplace transforms. It's one thing to understand the concept, and it's another to be able to execute it. So take some time as you prepare for the FE to practice problems like this, and we wish you luck. Have a good one.